Welcome to Code Along with Alex. This week, or I guess this session, we're going to be diving into Julia. And to get us started, let's just jump right into the docs. So you can see that we are just using the Julia Lang Getting Started page in the manual, and this is all available in the video description. Just check the description. I've also included some installation instructions for the Ubuntu operating system, also linked in the description. Um, just the process of downloading the binary, unzipping it, and then symbolically linking it on your machine so that it's nice and easy to invoke Julia. So installation instructions vary by your operating system, so I encourage you to check the julialang.org/downloads link for the instructions specific to your operating system. And for more help than just kind of a bunch of links, I encourage you to click the help. This is where I found out more information and got the commands. So I imagine there are similar installation instructions for different operating systems. So now that we have Julia installed and linked so that we can just easily run Julia, let's run some Julia. So I'm going to switch over to Termius, and we're going to just start the REPL, the interactive session with Julia. And to do that, you just have to run Julia. And this will only work if you've done this symbolic link. Otherwise, you have to run ./Julia from where you actually downloaded the file. In my case, that would be, where would that be? Oh, I'm in Julia. There's no ls in Julia. Yeah, so that would be oh yeah, in the bin, it'd be there. And so /, I guess I could cd in here and then do ./Julia. That's another way. But because we have the symlink set up, we don't have to mess with that kind of stuff. So let's just run it this way. Next, we can toggle back to the docs and just see kind of the syntax we're going to be working with. Full disclosure, I am not a Julia expert. I am very much a Julia novice. This is the first time I am exploring Julia, so we're going to learn together. I do have experience with other programming languages, namely Python, but with TypeScript, and I'm currently diving into Rust, but Julia is kind of this side quest to support my other engineering endeavors, so I'm excited for you to join me on this journey. So you can see that there's some simple integer addition that's capable, that Julia is capable of doing, and then there's some kind of built-in construct where the result of our addition is stored as this ans variable. So let's try that in our Julia locally. Interesting. So I suppose this just dynamically updates with the most recent result. Yeah, okay. Chill. Let's toggle back to the docs. So Yeah, the ands variable is only bound in interactive sessions not when Julia code is running otherwise. Okay, so the ands variable is only, yeah, the value of the last evaluated expression, whether it is shown or not. Okay, kind of what I guessed, but yeah, that makes total sense. But this is only valid in the REPL. So if you're running like a Julia file, like file.jl, the ands variable won't just magically work. We don't have a script.jl file, so I'm not going to run this command. But once we start building Julia programs, this will likely be how we run them. And like with many programming languages, you can also pass command line options. It's cool. And then there's also some help resources that the Julia team is sharing with us. And we can actually use the REPL as a learning resource by switching into help mode. I'm not going to do that right now, but I guess we could. Actually, why not? Let's go for it. It's fun. Oh, okay. Interesting. So you just, if you press shift slash, so i.e. the question mark, it toggles into this help mode. And then you're able to search for terms. Let me search for end, because the docs search for begin. Okay, and then we're returned some results and examples. So that's cool. Nothing revolutionary. Let's return to the docs. And then we're going to toggle over to variables. All right. So in Julia, a variable is a name associated or bound to a value. It's useful when you want to store value for later use. Maybe you did some math. It's usually some math. So let's do some examples with variables in Julia. I'm going to toggle back to Termius and clear some of this. I don't know that clear is a variable in Julia. Yeah, it's not. Whatever, it's fine. We'll keep it dirty. So let's create a variable named x and assign the value 10 to it. And the REPL automatically returns the value, prints it out. We can do math with those variables. So we should get 19. And then you can reassign variables, which is nice. Currently, I'm diving into Rust, and it's a little stricter about reassigning values. You have to declare whether things are mutable or not, but it seems like Julia is a little more like Python, where you can just like change things a little more fast and loose. So now we expect x to be 4. Nice. Okay, and then finally we can also change the type and place of variable. So if we say x, it's still 4. Now we can reassign x to be hello world, just a string. Julia provides a super flexible system for naming variables, which is kind of cool, but it's kind of a trip if you're not used to it. It's not just using like Roman or alphanumeric Roman characters like A through Z, 0 through 9. There's a little more flexibility with the kinds of namings or names you can use, which is super useful for like math equations and stuff if you're just trying to like represent things by their Greek symbol notation, as we'll see in a bit. But it can be kind of a mess sometimes if you see like emoji variables. It's kind of certain things are maybe not optimal, but In certain use cases, maybe that is. So let's name some variables and explore kind of the case sensitivity within Julia. So we got this float x. Let's create a signed integer called y. Next, uppercase Z, and this can be my sweet string. We can also have string variables declared using lowercase and underscores to separate words just for legibility or readability. Hello space. And then you're not limited to, like I said, like English letters and 0 through 9. There are options for using other alphabets, and we'll see very shortly the value that I copy paste from the docs, because I am incapable of reproducing this locally at the moment. But you can see we're able to store non Roman characters into variables. Like I alluded to previously, we can also have variables that are named using non-Roman characters, not just the actual value, but the name. And so it's another one I'll copy paste just because I don't know the keyboard shortcut off the top of my head. But you can use like lowercase delta. And then we nicely have a scientific notation returned to us. And then you can also use different languages. I believe this is Korean. Nice. But that's a little tricky if you don't have those characters available on your keyboard. So I'd say that just do things that are convenient, but in certain cases you need to use alternative or just non-Roman characters. They're not alternative. It's just, I mean, yeah, it's alternative. Yeah. Okay. So Julia or the Julia REPL and other Julia editing environments let you type many Unicode math symbols using the LaTeX symbol name or / LaTeX symbol name followed by tab. So this is kind of further tying into the mathy integration of Julia and how it lends itself to representing your code in ways that are perhaps similar to you as someone using formulas and like math formulas and even writing LaTeX for your manuscripts. So let's oh, it's nice. So like I kind of mentioned previously, the issue with Delta is like I don't have the keyboard shortcut remembered or like memorized. But apparently Julia is intelligent enough that we can use the LaTeX symbols to. Nice. That's super sweet. Okay. Yeah, I was about to say like how are you supposed to like I guess you could just like copy paste those things, but that's nice that it has this integration. Okay. Julia even lets you redefine built-in constants and functions if needed, but it's probably a bad idea. But so one of the main constants in math is pi, and so we can see the value here, 3.1415, bunch of digits, and then it's rounded, or it's just it stops because it's a lot of digits. So we can redefine pi to just be 3. Oh, it didn't like that. Interesting. Interesting. Okay. Okay, so yeah, oh, so because I already invoked pi, it it doesn't let you redeclare. Interesting. So that's some sort of like a stopgap measure, so you don't totally screw up your program. Okay. But I think I can, because I haven't invoked square root yet. Oh no, it's just not down. Interesting. Okay. Good to know. Not that I'm ever gonna do that, but like, yeah. So some more details about variables and naming conventions in Julia. You can see that uh, variables must begin with a letter, underscore, or a subset of Unicode. Code points greater than 0080. Not going to go into more details, but you can see the very specifics of limitations of variable names. But it's pretty flexible as compared to other languages, in my experience at least. And interesting. So apparently operators like the plus sign, addition, are also valid identifiers, but they're parsed specially. So sometimes operators can be used just like variables. Oh, so like parenthesis, the addition symbol in parentheses is like a function. Interesting. That's like funky for me coming from other languages, but I get it for just being like really terse and compact. That's nice. Um, okay. Damn. Yeah, Julia's a trip. It's a little weird. I mean, not bad. It's just different. It's interesting. I mean, this is different than. I mean, like I thought Rust was different, and it is, but this is like different in a different. This is different in a its own particular unique way. Um, yeah. Okay. Let's do some more coding. So um, before we do that, let's read the sentence or two. A class of variable names, or a particular class of variable names, is one that contains only underscores. These identifiers can only be assigned values, but cannot be used to assign values to other variables. More technically, they can only be used as an L value, but not an R value. Okay, what the heck is that? Interesting. Okay. Interesting. Learning some computer science stuff. All right. Let's code this out and see what happens. I kind of learned with the error codes and resolving them in addition to reading. So let's break some stuff. So we got X, triple underscore, size. Ooh, no commas, just space delimited. Different. Okay. So it's like we're throwing away the second component of size, or is this a very yeah, no. Okay. Yeah, so we just like dumped it basically. Okay. Because yeah, that makes sense then. So you can't assign y to that because there's no that. Okay. And then only explicitly disallowed names for variables are the names of the built-in keywords. So like you can't use else or try as a variable name. Like it'll just be like nah, dude. Yeah, nah. Unexpected L, same thing. Try equals, nah, dude. Yeah, not into it. Not into unexpected equal sign. Not cool. Okay. So, some Unicode characters are considered to be equivalent in identifiers, so this can be tricky. And so, Julia handles this, I guess, using the NFC normalization. If you're curious about that, dive into it. I'm not that curious, so I'm not going to dive into it. But yeah, there's some cases where it looks like epsilon and mu are treated as equivalent to the corresponding Greek letters. Oh, interesting. So there's like some weird equivalencies. Okay, whatever. It's like not a big deal. And then just some stylistic conventions. Interesting. So use of underscores to separate words is discouraged unless it would be hard to read the word otherwise. So I guess that's a place for subjectivity in naming, but that's not a big deal. Okay. Let's briefly take a drink of water. Hydration is important, and let's get going. So now we're going to move on to integers and floating point numbers. So we can see integers and floating point values are the basic building blocks of arithmetic and computation. So the built-in representations of these values are called numeric primitives. And then representations of integers and floating point numbers as immediate values in code are known as numeric literals. So 1 is an integer literal, while 1.0 is a floating point literal. And then their binary in-memory representations are numeric primitives. Okay. So Julia has a lot of primitives available of the numeric varietal, and then a complement of arithmetic and bitwise operators and mathematical functions defined over those numeric types. Sweet. So much math. Next, Julia can take full advantage of the computational resources of modern computers because it seems like these functions map directly onto the numeric types and operations natively supported on said modern computers. So that's nice. Cool. And then some additional stuff about support for arbitrary precision. Not too interesting. Here's a table of the primitive types. Don't need to memorize this, but it's kind of standard. Integer and unsigned integer of different bit depths. The kind of standard 8, 16, 32, 64, 128. Boolean, floats, like it's the standard stuff. And cool, complex and rational numbers in addition to standard floating point and integers. So now that we've read a bunch of stuff, let's actually code some numbers again because that's more fun, or it's fun in a different way. Sweet. So if you just put in 1, you get 1 back. Same thing with 1, 2, 3, 4. You get 1, 2, 3, 4. It's not like, yeah, cool. Default type for integer literal depends on whether the target system has a 32-bit or 64-bit architecture. And so I believe I have a 64-bit architecture on this device. Yeah, int 64. If you have a 32-bit system, your result will be int 32. The Julia internal variable sys word size indicates whether the target system is 32-bit or 64-bit. So that's another way, instead of hackily checking the type of an integer. So you can just Nice. Autocomplete is active with tab or tab complete. And yeah, 64-bit. Julia also defines the types int and uint, so integer and unsigned integer, which are aliases for the system's signed and unsigned native integer types, respectively. So if you're on a 32-bit, it'll be int32, vice versa. Awesome. And then larger integer literals that cannot be represented only using 32 bits, but can be represented in 64 bits, always create 64-bit integers, regardless of the system type. And so this example is kind of less exciting on a 64-bit system, but if you were on a 32-bit, you'd see int64, I guess, which is thrilling. Okay. So kind of relevant to more blockchain, Web3, decentralized infrastructure space. I'm seeing some hexadecimal digits. The OX prefix. So let's go. Cryptography. You can see the type of our integer. It's still an unsigned integer 8, but it just has the prefix OX. So if we do x equals OX123, we'll see that now it should be a different integer type because it's a larger value, requires more bit depth to be represented. So you can see it went from 8 to 16. And this kind of trend continues. If you increase the size of x or whatever your arbitrary variable name is, and you're additionally not limited by digits, you can, or integers, you can also put in characters. So this is like, you could imagine a wallet address. And then if we just see type of x, you'd see it's now type 64. And then, yeah, I'll leave you to try the final example of uint 128 by yourself. But yeah, it just says uint 128. Okay, so just some more follow-up text from the Julia writing team. This uint bit depth scaling that we just saw is based on the observation that when one uses unsigned hex literals for integer values, one typically is using them to represent a fixed numeric byte sequence rather than just an integer value. That was over my head a little bit. Let me try to understand that again. So the size of the unsigned value is determined by the number of hex digits used. Okay. And so that behavior is based on the observation that when one uses unsigned hex literals for integer values, okay, one typically is using them to represent a fixed number byte sequence rather than just an integer value. Yeah, that's true. Okay. Took me a second, had to read it a few times. It's starting to ingrain. Cool. Okay, and you can see binary and octoliterals are supported in addition to the hexadecimal literals. So we can also declare, instead of OX, we can do OB. Got the equal sign. Oh, wow. Interesting. And so then it returns it as the hexadecimal representation. But then if we do the type of it, it's a uint8. Okay. And then we can do the same thing with an octal variable. I did not. It's O. Oh. Okay, that's octal. And then if we do type of that, uint8. And then finally, we'll do x equals ox. Bunch of O's. A few ones, 2s, and 3s for good measure. Weird. And then can we do type of x? Big int. Oh, because it's so big. Okay. So as for hexadecimal literals, binary and octal literals produce unsigned integer types. We just saw that. And the size of the binary item is the minimal size needed if the leading digit of the literal is not 0. In the case of leading zeros, the size is determined by the minimal needed size for a literal, which is the same length, but leading digit 1. Okay, and then it's just showing some kind of anecdotal examples, or actual, not they're real examples. Okay. Interesting. Yeah, so 0x1 and 0x12 are uint8 literals, while 0x123 and 0x1234 are uint16. And then they just kind of show how that scales up. And then even if there are leading 0 digits which don't contribute to the value, they count for determining storage size of a literal. So 0x01 is uint8, while 0x0001 is uint16. Okay, so that makes sense why I got big int for that number, because it was just a ton of zeros, and that counts towards the storage size. And the values which cannot be stored in uint128 cannot be written as such literals. Okay. And then talking about signs. But instead of representing binary, octal, and hexadecimal literals with a sign, it looks like Julia is using the 2's complement of the value. So negative 0x2. Yeah, and then negative 0x0002. Okay. Oh, I didn't toggle. Forgot I was on the docs, but ran those 2 examples, and you can see how they were transformed. Minimum and maximum representable values of primitive numeric types, such as integers, are given by the type min and type max function. So this just kind of gives you the range. Okay. So because of the 0, it's 1 less on the positive side. It's not negative 2, blah, blah, 648 to positive 648. The 0 counts for 1. Okay. And then if we're feeling real tricky, we can write a for loop to print out the type min and type max of each of these data types that I'm gonna input right now. So we start integer 8, int 16, int 32, int 64, int 128. And then I'm lazy, so I'm just going to copy paste the dang. I screwed myself up. All right, we're just going to not do all of them. It is what it is. We'll just do this 8 and 16 for both uint and int. And then for t and this array, print ln. Ooh, it's like Rust. Interesting. And then we're going to do some string interpolation. And so we're going to lpad. Interesting. Maybe that spaces out the result just so that it looks pretty. Yeah, and then t is each of the types. So we're padding each of these types by, I guess, maybe 7 spaces. Or just so the width is... Let's look up Julia lpad. That's not that important. But then you can see we're interpolating with the type min and type max for t. I guess you can't see this because I forgot to toggle, so apologies. But if you're looking at the docs with me, you'll know what I'm talking about. So we got t7. Let's get a colon up in here. Now we can start the interpolation with type min and type max of t. Another $sign up in there. T. Then close it out with a bracket, a quote, another parentheses. What is that word? And then with an end. Boom. And you can see for the 4 types that we input into that t array, or into that array, each one outputted the type min and type max. So that's kind of cool. It makes sense that the integer with signs is kind of reflected across 0, whereas the unsigned integer starts at 0 and scales up to the positive. Very cool. So now we're going to move on to overflow behavior. So in Julia, exceeding the maximum representable value of a given type results in wraparound behavior. So we can explore this concept using the type max function that we just explored. But let's do 16 instead. Type max 16, so we can see that it's a little over 32,000 and change. So then if we do x plus 1, it's not going to just go up magically to 32768 because that's outside the bounds of the int16 type as declared by the type max. So we expect it to, I guess, go to the type min of int16. And based off of the previous command that we ran, I expect that number to be negative 32768. But let's see if if my expectation meets reality. It's not. It's interesting. What? Let's try that with the example declared in the docs because this did not behave as I expected. Okay, so that's a big number. X plus 1. Is this going to be a negative number or are the docs just off? Interesting. So I guess the int16, it just okay, let me try this again. x plus 1. Now let's do type of x. X equals x plus 1. Type of x. Okay, yeah, so I've resized that. Okay. Now I get, okay. So or arithmetic in Julia with integers is a form of modular arithmetic, and it reflects the characteristics of the underlying arithmetic of integers as implemented on modern computers. Exciting. So when overflow is possible, explicit checking for wraparound produced by overflow is essential. Otherwise, the big int type is recommended instead for big numbers. So we can look at that. If we just do 10 raised to the 19th power, you can see how it wrapped around, and it's a negative number, which is not mathematically correct. It's an artifact of the computers. So if we prepend the 10 with a big, we then get a big number, a big int. So this brief aside about division errors. Integer division has two exceptional cases: dividing by 0 and dividing by the lowest negative number by negative 1, excuse me. And both of these cases throw a divide error. And then the remainder and modulus functions throw a divide error when their second argument is 0. So let's try that real fast. So if we get 10 divided by 0, it's infinity. How do you implement the div? Is it just like div 10, 10, 0? Integer division error. Yeah, okay. So then, is this just going to be 5? Yeah, sweet. So, the lowest negative number. So then, what if we do div type min int 16 int 64? 16 was giving us a grief. And then negative 1. Interesting. Oh yeah, because the type min of int 64 is like that real big number ending in an 8. But then the type max ends in a 7. So if you divide by negative 1, it's out of the bounds. Okay. So that's enough with integers. Now I'll take a sip of water and move on to floats. Cool. So let's add some decimal points on these numbers. So we got a 1.0. If we don't add a 0 after the decimal point, Julia just does it for us. Same thing with if we don't add a leading 0. You can see the same thing applies with negative values, except a 0 is added in front. If you're just using a negative value above 1, then it doesn't automatically throw a 0, a leading 0. Same thing, scientific notation. That throws a trailing 0 after a decimal point. Even if you're putting an integer, it'll cast it as like 4.0. Then for smaller numbers, it'll return it as decimal representation. if you pass in the scientific notation. And so these results were all float 64 values. And then literal float 32 values can be entered by passing an F in place of an E when you're doing scientific notation. So like if you did 0.5 E, I guess that doesn't make any sense, or E0, that would just be 0.5. And then if you do 0.5 F0, okay. So I'll make this one X equals, and then Y equals this one. And so then like, let's do type of X, type of Y. Oh, okay, interesting. And then you can convert float 32, or you can convert a value to float 32 by passing the float 32, I guess, function. So let's get the type of X if we cast it to float 32. Nice. Can we cast float 30 or float 64 to float 32? So that would be type Y 64. Will this break? Oh, okay. Cool. So hexadecimal floating point literals are also valid, but only as float 64 values with P preceding the base 2 exponent. Interesting. So you can see how this kind of this slightly more sophisticated syntax to manage different, I guess, encoding types. So an example of that, 0, 1, or 0x1 P0, 0x1.8 P3. Yeah, that's weird. All right, I don't like that. There's also something called half precision floating point numbers, and they're supported, float 16, but they're implemented in software and use float 32 for calculations. I'm going to skip that just because it's not super exciting. And then finally, you can also use underscores as a digit separator to help with readability. So 10,000 and 10,000, which is kind of cool. Okay. Getting there. It's a lot about floating points. There's a lot about numbers, I guess, but I guess Julia's about numbers. Okay, so floating point 0. Does 0.0 equal negative 0.0? I guess it does. It's weird. But they have different binary representations. Funky. So bit string 0.0. Bit string negative 0.0. Wonky. So Julia has some special floating point values. These are, I guess, 3 specified values that do not correspond to any point on the real number line. They're just kind of there, I guess, convenience. So there's a float 16 infinity, a float 32 infinity, and a float 64 infinity. Also negative infinity equivalents, and then nan, not a number. So I guess that's nice depending on the type of arithmetic bit depth required by your program. You got options. And there's more in-depth discussion of this topic in the numeric comparisons link in the docs. But yeah, now we can move on to some infinity examples. Not super exciting, but just really trying to build some muscle memory for Julia, how it's different than other programming languages, how it's similar. Just get the quirks. Everything has its quirks, but some are quirkier than others. So far, Julia is a little quirky. Not bad, just different. I'm not going to do all these, but I'll try a few. It's weird. Okay. Had enough of that. Okay. And then to tie it all together, we can see the type min of a float 64, which we expect to be negative infinity. Cool. So if we toggle back to the documentation, you can see that now we're pivoting to machine epsilon, which is not something I'm familiar with. So most real numbers cannot be represented exactly with floating point numbers, and so for many purposes, it's important to know the distance between two adjacent representable floating point numbers, which is often known as machine epsilon. Interesting. Okay, so upper bound on the relative approximation error due to rounding in floating point arithmetic. Okay, that makes sense. More than this. So Julia provides the EPS function or keyword to give the distance between one and the next larger representable floating point value. Okay, let's do some EPS. It's like, what's EPS of 0? Okay, so that's not a thing. Oh, because they're integers. My bad. So what about 0.0? Okay. Oops. Interesting. I keep wanting to touch the I. Some kind of muscle memory. No, it's not an integer. It's a float. Okay. So EPS is a thing. And the distance between two adjacent representable floating point numbers is not constant, but is smaller for smaller values and larger for larger values. Okay. In other words, the representable floating point numbers are densest in the real number line near 0 and grow sparser exponentially as one moves farther away from 0. Yeah, this is a math programming language. By definition, EPS of 1.0 is the same as EPS of float 64 since 1.0 is a 64-bit floating point value. Okay. And then Julia provides some other convenience functions, next float and previous float, or prev float, to return the next largest or smallest representable floating point number to the argument respectively. I'm going to skip this because it's kind of dull, but dive in if you're curious. Okay. Some information about rounding. Just approximation of floating points, and then the mode for rounding. Here's some more details about the subtleties of floating point arithmetic, which is kind of outside the scope of this session, but if you're fascinated by this kind of deep dive into very specific technical topics, then I encourage you to dive in. I'd rather code right now. So let's keep scrolling. Usually I try to do most examples, but a lot of this is kind of just reading. And my throat's getting dry. So on that note, I should have some more water. Cheers. Okay. Satisfying gulp. All right, so there's some constructors for convenience. We can skip this. It's really just like a lot of type, going to the weeds of types, which is chill, but I don't need this right now. Right. Oh, interesting. So we can actually like do math pretty easily with Julia, which I kind of want to try. That's a little interesting to me. So we can declare variables like x equals 17. And then we can write some kind of formula and have that compute on our declared x value, which is pretty sweet. Let's add, let's subtract 8. It's way bigger than I expected. Oh, that's nice. And then you can also do stuff like 2 root 1.1. Oh, nice. Okay. I like it. Picasso. So yeah, this really does feel like math as code. I know like with Python there's the SymPy library, but this just seems like a different kind of beast. Like it's just that is the primary focus of Julia, which makes sense. I mean for like simulations and optimization, like it's all math. I mean everything is math and coding, but like that's math heavy for the coder. Like they're programming mathematical things, whereas like other programmers are doing maybe data pipelines, which are less formula focused. There's functions, but I feel like formulas and functions are very different. Okay. That was a whirlwind tour of variables. Let's see how big the mathematical operations section is in elementary functions. This could be more interesting. It's not too long, is it? A lot of sections. Damn, I want to have fun with Julia. It's kind of boring. It's all right. Part of learning can be boring sometimes, which is just part of the process. So acknowledging that is okay. So let's do a little more Julia. Let's get through this section. So we can do some arithmetic and bitwise operations across all of our numeric primitive types. And then there's also a bunch of efficient implementations of math functions for us. Sweet. So you can see some of these arithmetic operators, unary, binary, plus and minus for both, times their multiplication, division, integer, multiplication and division, power, remainder. Pretty standard. We did a bunch of this in the previous example, so I'm going to skip through some of these, especially the more simple like 1 + 1 kind of stuff. All right, some Boolean operators. Negation. This is pretty standard, like in other programming languages. Like Python has this kind of syntax. Short circuiting and short circuiting or. I'm also familiar with this kind of stuff. Okay. bitwise operators. Nothing mind-blowing, but get the idea. Depending on your use case, this could be helpful or not. But yeah, I'm gonna skip over those. Okay. I like that Julia has the same kind of shorthand notation for updating a value in place with like plus equals or minus equals or times equals. That's just convenient. Yeah, updating operators. But yeah, just to note that updating a variable can potentially induce a type change, but that just depends. And back to the math, we got some vectorized dot operators. So dot up caret automatically defined to perform up caret element by element on arrays. So, oh, interesting. So like the array 1, 2, 3 raised to the 3 is not defined because there's no standard math to like cube an array that isn't square, because it's like a 3 by 1 array. But using vectorized dot operators, we can throw a period on that, and then Julia's smart enough, and it'll throw that math across or it'll apply the math across each element in the array, which is pretty cool. I'm gonna try that in Julia. That's kind of snazzy, to be honest. I dig it. So we expect this to break. Yeah. But then if we do a period before this, nice. That's clean. Back to the docs. I like that. That's super convenient. So it's parsed as the dot call. A broadcast operation. Okay. I've heard that term before. Very nice. And the docs are just showing some more advanced examples of how you can apply these dot operators. Kind of chaining them together, using them. Interesting. So you can also use the dot syntax with user-defined operators. That's nice. Do this similar kind of broadcasting of your function across, or your operator across an array. So there's comparisons like other languages. It's very familiar. I'm gonna glance over these simple examples just because it's like one is greater than 2, less than 2, true. Yeah. But it's just like basic math comparisons. And they're showing you some of the behind the curtain. These comparisons are done using bits for integers, and then for floating points, it's using the IEEE 754 standard. Okay. And then there's some functions to test numbers for special values. So there's like an equivalency function is equal, a finite function to check if it's finite versus if it's infinite or not a number. And nice that you can do nan equals nan, so you can almost have like a not a number check where you're just running it across your value and you just hard code in nan. But there's also the isnan, so I guess I wouldn't be surprised if isnan just implements is equal behind the scenes. Okay, now you can, unlike most languages, comparisons can be arbitrarily chained, with the notable exception of Python. Yeah, Python rocks. Okay. So that's a real nasty kind of expression, but got the idea. This is kind of a trivial example. It's not particularly useful, but in certain cases, it is very useful to have chained comparisons. So let's do a quick such example. Toggle back to VS Code, or no, it's not VS Code, it's Termius. Let's declare a function called v of x, and it'll return a line with x and then x. Cool. Now, what happens if we do like v of 1? Doesn't like that. What if I do v of 1 is less than v of 2? That's why my variable is print ln. There we go. Okay, so for v1 it returns first just it prints x and then it returns x. Now let's do v1 less than v of 2. 1, 2 true. What about greater? False. 1, 2 false. Okay. Back to the docs. So there's elementary functions. They can be applied in vectorized fashions. Cool. It's kind of a short section without too much context, but oh well. Next, we can look at operator precedence and associativity. Just kind of order of operations from highest precedence to lowest precedence. I'm not going to read through all these just because that's kind of too much, but if you're struggling with your program code and running into issues that might be around this area, then maybe this table is helpful for you. And there's more, I guess the comprehensive list of operators precedence is located in the source juliaparser.scm file. Okay. Interesting. So you can like do a line break, or not a line break, but like a logic break with a semicolon, and then pass in, so like declare a variable, semicolon, logic break, and then you can do 23x minus 1,000. Cool. You can do some numerical conversions. We did a little bit of this typecasting earlier, but I guess this section will go more in depth. You can see how rounding is applied to values. Now you can typecast different values, basically, or converting between them. Nothing super exciting, so let's keep going. Some rounding functions, useful for doing math and handling the particulars of your logic, whether you want to do floor, ceiling, truncate, or good old round. Really just kind of a table of functions related to division. I'm not going to click on all these, but you can dive into the specifics as you like, and I'm sure as we continue with our Julia journey, we'll get some exposure to these different functions. Absolute value, signs, change the sign. Okay, and then just more mathematical operators like square root, cube root, hypotenuse of a right angle. Dang, these, okay, so this is math. But yeah, this is super helpful that these are like convenience functions built in from the get-go, and users don't need to declare them by themselves or import some library. It's just ready to go. And we got trigonometric and hyperbolic functions like sine, cosine, arctangent, secant. So cool. Whatever your trigonometric needs are, you're good to go. So on that note, I think this is kind of a healthy stopping point. This was a little more reading than I was expecting, but I think it'll be good to get through this kind of text and just build more familiarity with Julia, slowly dive into more applied examples, and then ultimately get our hands dirty with AutoAgora and allocation opt for really just fine-tuning our indexer operations and becoming just really performant indexers on the Graph Protocol network. So with that, I just want to say thanks for hanging out, looking at a bunch of math text with me today. But I really appreciate your company and just spending the time to learn with me. So thanks, and I'll see you next time on Code Along with Alex.